Thank you very much. Now I'm going to give you an overview of the basics, the fundamentals of the EMMO. So the idea upon which we build the European material modeling ontologies. But before digging into the ontology, I would like to remind you what are the scope of the EMMC and why we decided to go in the direction of building an ontology. The idea is that we need to find a way to establish a common terminology in terms of concept and vocabulary in materials modeling that will lead to greatly simplify and much more efficient communication between the material experts that are involved in the modeling of materials. Is to try to find a common language between phenomena, between scale, between software, and also solver, and facilitate the communication and the expression of the user case that each stakeholder has. The ontology is based on previous work, mainly the review of materials modeling, the workshop agreement that we had in the past month between several European organizations, and the work that has been done in order to categorize the modeling examples found in the European project in a template that is called MODA. What comes from the review of material modeling is the finding that we can categorize the models and the entity in 4 big classes, which are electronic models, atomistic models, mesoscopic models, and continuous models, each one with its own particular class of entities that stands for real material entities that we use in material science. The MODA, as I told you, are tables in which for each particular simulation, one user can list and describe the type of models that they use in connection, and for each model they can express in a standard way the material type, the geometry, time lapse, and more in detail also the equation, the physical quantity, the material relation that they use in a particular model. We try to include all these aspects inside the ontology. Another important point that we need to address within the ontology is also the possibility to express and to represent the multi-scale modeling, which comes as linking of coupling of several models applied to several entities and are expressed in this workflow that has been standardized within the MODA. At this link you can find also the workshop agreement in its final form with a strict definition of the fundamental terms that has been used in the models, has been used in the MODA we used to build this ontology. This is the first step towards standardization of the vocabulary and the terms in materials modeling. So, as I told you, all these materials, all these previous work, previous findings, we try to include inside the European materials modeling ontology. So the ontology should be a way to, a tool to represent in a standard way the material user case that we want to deal with. So our device, our material, our process, the physics law that describe our material, our process, our device, the physics law, which can be expressed by equation, must be can be represented by physical models, and then they can be used in a simulation software that includes solvers and post-processing. And the ontology should facilitate the connection between the choice of a particular model and the choice of a particular software. The building of the EMMO is a strongly multidisciplinary effort. It's done within the EMMC, and we want to represent, as I told you before, a standard representational framework, the ontology itself, that is based on current materials modeling knowledge. In order to do so, we need to work in the field of physical sciences, because this is the knowledge that we want to represent and we want to formalize inside the ontology. We need to use the findings of analytical philosophy in terms of merotopology, semiotics, logic. We need to also work in the field of information and communication technologies, because the most powerful way to express and to use the ontology is within a digital platform. So, what is the place of the EMMO within the real world and the user? Here you can find a diagram in which I'm trying to show you what's the place of the ontology. We start with a physical entity in which we are interested in, as I told you, a material, a device, a process. This is the physical world, the object. Then the expert is looking at it, and it represents internally in its brain, for example, what he is looking at, and he starts to reason about this object that he represents inside this head. The expert is called the interpreter. It can be a human being or a machine that can recognize object attributes. And the interpretant is the internal representation that is created by the human being or the machine to connect the object to its brain. As you can easily understand, the interpretant cannot be shared between human beings because it's the internal representation. But what we can share is the sign that stands for the interpretant and then to the object of the physical entity. So the ontology itself is a way to represent things in a standard way, so that we can look at the sign and immediately find a way to build our internal representation of the object. So we have the object itself. We have the active agent, which is the interpreter, who looks at the reality, and then we have the ontology world, which is a system of sign, a representational system that helps to share the knowledge that the interpreter has about the object. This has a strong intersection with the theory of semiotics. The ontology world lives in is expressed by using, for example, the OWL language, by using C++ class hierarchy, in a textbook, for example. There are several ways to represent the ontology. What are the elements of the ontology that we use in the EMMO? First of all, we have the individuals. The individuals are, you can call it sign, semeion, which is sign in Greek, simulacra, picture, whatever you want. There are signs that stands for a particular real object. the connection between the real object and the sign is always done by an interpreter, by an active agent that can say that the sign A stands for this type of object. Another important, and this is okay. Then we have classes. Classes are primitive elements that are also known as collection or sets. Is something that we use always when we want to express with a single sign a bunch of other elements. Classes themselves are primitive elements. And also we need to have actions. Actions are the proposition in a logical framework, and the logical framework can be different. We have several choices of logical framework that can be used that define the relation between ontology elements, between individuals and classes. So we have our individuals, we have a way to define classes or sets of these individuals, and we have a way to define relations between classes or between individuals and between classes and individuals thanks to actions. These elements are the building block that we want to use in order to represent the knowledge in materials modeling. They are primitive in the sense that are given and not defined. It's something that we naturally have and cannot be strictly defined. So there is a strong multidisciplinary intersection with analytical philosophy and also with ICT in terms of digital implementation and reasoning. When we start to have a set of action, we need to use an automatic reasoner in order to deal with all the implications of the action that we define, for example. And this is done by within the digital implementation of the ontology. So how to use the ontology? The individuals are not simple. They are not they can be, of course, a simple sign, for example, a letter that stands for the flower. But individuals in an ontology are not so simple. You can attach to each individual attributes in form of actions that are defined by the user upon declaration. So the interpreter looks at its object and then creates a sign that stands for the object, and also provides the actions that gives the properties to the individuals that fits as much as possible the property of the real object. The actions are used to categorize individual in classes, and an individual in an ontology are logical picture of the real world entity. You can see here, for example, 3 individuals, A, B, C, flower, yellow car, and red car, A, B, C, and depending on the properties, you can define classes that are collects individual by attributes. For example, this class yellow thing is the class of everything that has color yellow, and the class car is the class of everything that is a car. This is a way in which that we use to express the knowledge in an ontology. So let's try to give a definition of the EMMO. It is simply a representational framework of predefined classes and actions, so it is an ontology. The EMMO is provided by experts, so there is somebody who try to infuse the knowledge in this ontology. This will enable end users, so industry, research, academy, everybody who deals with materials and modeling and also characterization, enables end users to represent real-life physical entities, materials, devices, processes, models, and properties using ontological signs in a standard way to facilitate interaction and exchanges between all involved material modeling and characterization communities and stakeholders. So what the EMMO provides? The EMMO does provide the consistency of the symbolic representation. It means that it will help you to build signs with properties and parts that are consistent with what the EMMC think is the right way to build a representation of the world. For example, we have here a cat. We can say that a cat has a proboscis and an arm. We can say that, but the EMMO should prevent you to do that because it's not consistent with the knowledge that we want to infuse in our ontology. There can be other ontologies in which this can be allowed. For example, an ontology of used to build a fantasy book, for example. But in the MMO, we need to have rules that prevent, for example, for a molecule to be part of an atom. This is not possible. This must be prevented by the ontology. But what the EMMO does not guarantee is that the representation that you build in the ontology is always connected to existing physical entity. For example, in the physical world, if you have this representation in the ontology world of a cat eating its food, we are not sure that in the real physical world we have the cat or the food. So the ontology can be used to build a representation of things that are reasonable to exist but not necessarily exist. So if we define a lie as something that can possibly exist in a defined space and time in the real world but not actually exist, then we can distinguish between material characterization and materials modeling. While the EMMO can be used in material characterization to describe properties of real entities, because we measure, for example, the property of fullerene, of graphene, of a particular material, of steel, and so on, in material characterization, we are sure that the properties that we provide and we standardize within the EMMO are actually properties that have been collected from a real existing entity. In materials modeling, this is not the way it works. In materials modeling, we create lies using the EMMO. But if the ontology is good, the lie is so good that may be proven to be true. Because within the EMMO, we have an idea, we develop the idea, and we should be able to come back to the real world and prove that what we build within our ontology can be actually built in the physical world. So materialization is using the ontology to tell the truth about the world, and in materials modeling we build lies or possibilities, and then we use the ontology to work with these lies, and in the end we will prove that these lies can be true. This has been stated by Umberto Eco while defining semiotics, which is the theory of science, which is a discipline studying everything which can be used in order to lie. If something cannot be used to tell a lie, conversely, it cannot be used to tell the truth. It can in fact be used to tell at all. So the EMMO is constructed to be a perfect lie design tool. It will help you to build the perfect lie, because what you say in the EMMO, even if it does not exist really, it can exist, because the knowledge that we infused in the ontology is so good, at least it should be so good, to make you build only truthful representation. So main objectives are to provide, the EMMO main objectives are to provide a basic framework for description of materials, to provide an efficient representation of physical entities by using granularity levels to facilitate multi-scale materials modeling and characterization. Granularity levels means that we should be able to decompose each material in its constituent in order to enable the possibility to use several models that focus on different scales for the same material. We need to include in the ontology the physical models and also their relation with the material entities. The ontology should categorize material properties to facilitate standardization of material characterization and model validation. It should also provide an interoperability framework for material properties database. We started with this ontology by clearly separating the concept of set and the concept of item. So the root of every class in the EMMO is the class entity. This is a class representing the collection of all the individuals, signs that are used in the ontology. So every sign that we use inside the EMMO is an entity. And then we separate entities in two big classes. The set, which is the class representing the collection of all the individuals, the sign that represents a collection of items, and item, which is the class that collects all the individuals that are members of a set. So item is the most comprehensive set of individuals. Items are not entities in order to avoid Russell's paradox. So this accordingly to the Zermelo theory of Zermelo set theory. The item class is an individual of set. So one individual of set is a class of item, and also a subclass of item are individual of set. So in this sense, set is a meta class that can be used to contain the ontology, all the sub level of the EMMO under item. So by separating set and item, we clearly distinguish between the membership set theory and the mereology. So the fusion, the merological theory. A set is declared using member primitive relation. So a set of individuals keeps its membership distinct and is a further entity over and above them. So the set of men is not a man itself. So a set of human beings is not a human being, is an individual of this class. A set is not the same and is not of the same entity types of its member, and a set individual has a determinate number of members. While in fusion, so the items are based on as-part merological relation that can be axiomatically defined. So a fusion is the sum of its parts. So a car is made of several mechanical parts. A molecule is made of nuclei and electrons. So in this sense, a car is not a set of parts, it's a fusion of parts. If you separate the parts and they are no more a car, then these parts are members of a set if you want to create the set of the parts that can be used to build a car, for example. A fusion is of the same entity type as its part. So if you have a material entity, its parts must be material entities. So this difference between membership and parthood is the main distinction that we provide within the EMMO, and this is something that we needed to have, and it is not very well prescribed in the basic formal ontology. The mereology itself is a field of philosophy that provides you with a very well-defined set of actions that can be extended in order to build several mereology theories that may be or not useful for our purposes. we decide to use this type of actions to define the mereological properties of in the EMMO. And the idea is that we will make strong use of the proper partud, which have the properties of so X is proper part of epsilon only if X cannot be superimposed to epsilon. And we also use the strong supplementation action that is used in mereology to define a particular, a very generic, very basic set of action and a very basic mereological theory. You can find a lot of information in the book of Casati-Varzi, Parts and Places, which is a reference point for mereology. We also want to use the topology and to connect topology and mereology in a single field, which is called merotopology. You can find in Parts and Places also a very nice introduction to this topic. The idea is also to use the property of connection. So connection between parts X and epsilon is defined by this type of relation, and we can merge the mereology and topology by defining a particular action that is based on the notion of enclosure, that is based itself on the definition of connection. You can I don't want to spend more time on this, but you can find in these slides the basic concept, and you can find in this book the more insights if you want. So up to now we defined set, item, and we introduced the merotopological system that we want to use to build the EMMO. But what is the most general type of item that we have in the real world? We in order to define that, we define the substrate. The substrate is the place in general sense in which every real world item exists. A substrate provides a dimension of existence for real world entity. It's a merotopological entity. It's the place, the physical place in which you put a real life entity. Substrates are always topologically connected spaces. A topological space X is said to be disconnected if it is a union of two disjoint non-empty open set. Otherwise, X is said to be connected. This follows the Kantian definition that intuition, that space and time are a priori form of intuition. So everything must be in space and time. So these are examples of substrate. Substrate must be connected. So this is a connected space. B is a connected space. C is a connected space. D is a connected space. These are not connected. So the idea of substrate is that you have a connected a place in which you can position, you can define your material entity, and this place must be connected in topological sense. But what type of substrate we can have? We can have the substrate in which we live is the space-time. Space-time that we call hybrid substrate, because hybrid means that it unfolds in space and time. Space is another type of substrate which does not unfold in time, and time is another substrate that does not unfold in space. And each type of substrate has its own particular subset. We are interested mostly in hybrid because it is the place in which we live. But we want also to define other type of subset because sometimes we need to define geometrical entities. For example, the surface between two material entities, and a surface that evolves in time. So a surface that evolves in time is a world volume, for example. You have a surface that evolves in time, it's called world volume. It is hybrid because it's a surface that extends also in the time dimension. The same is, for example, if you want to define a line in a space that evolves in time, it is a world sheet, hybrid. And that's all. This is the idea. All the material that we deal with will be in space-time. So the material entity branch of the EMMO is under space-time. But if we want to deal with geometrical entities that are not slice of a space-time, then we need to put the slice inside these other classes. It's important to notice that since we are in a part of the hierarchy, each branch of item can only have parts of the same type. So if you have partout of a word line, it is always a word line. The boundary of a substrate is not part of it, but is a slice, topological relation. So we define a slice as a part with lower dimension. So the partout, the mereology, cannot move object from its classes, but the slicing move objects from one class to another class. So partout is only between subsets of the same dimension. This restriction in the mereological relation is done in order to overcome a typical misuse of the partitioning procedure that occurs when the user wants to stretch the is part of relation beyond its applicability limit. Let's make an example. You can slice a 3D plus 1D cake, so a 3D cake in time, in 3D plus 1D thin parts, but it's impossible to slice the cake in infinitely thin 2D plus 1D slice. You cannot create a piece of cake which is 2D in space. You cannot. So in the EMMO, materials are always 3D plus 1D. 3D in space and 1D in time. If you want to slice your cake in 2D plus 1 slices, then it is no more a cake. It's a region of space, which is a slice of space-time that you use to define a place, but not a material. So we strictly separate the mereological partout and the slicing. Mereology is partout is under mereology, while slicing is under topology. This is the hierarchy of the properties that we use to deal with the space-time entity. This is an example of space-time entity. It is also only in one spatial dimension and in time. We have the enclosure, which is the root of the properties. We have the partout and the slicing. Partout and slicing. This is mereology. This is topology. Spatial part is a part of the whole in which you have the part extends for all the life of the object, and the temporal partout is a part that extends on the whole spatial extension of the object. So this is a subset in time of the whole object, and this is a part of the object that exists all the time the whole exists. Then if we move to the topology branch, we have a time slice, space slice, and projection, and you can see here that we reduce the dimensionality of the whole, because slicing is exactly what it does. So if you have a material, you can only apply mereology and having parts which are materials. But if you apply a slice to a material, you no more have a material, you have a geometrical entity. It seems trivial, but it is not. The EMMO basic assumption is that the real world manifests itself as a one space-time entity, the universe. Some mereological part of the universe express peculiar properties that can be perceived by an interpreter ontologies. These parts can be categorized in matter or field. So we perceive the world by interacting with matter or interacting with field. For example, matter, everything you have on your desk, for example, and field, the gravitational field, for example. Matter is a subclass of space-time that expresses some mass property. Field is a subclass of space-time that can be perceived by the ontologies but expresses no mass property. So real world entities are always subclass of space-time. The real world entity is a space-time entity. But how can we start to categorize the material world? Well, we move as a first step. We move towards the elementary particles because it's the easiest way to define objects that are well defined in space and in properties. So the first thing that we need to define are the elementary particles, which are a subclass of space-time called elementary, whose proper parts can be only temporal parts. It means that you cannot have space parts of elementaries. You can only have interval of the life of elementaries, but not divide them spatially. So the atomic level, atomic in a philosophical science, which means that atomos cannot be divided, is defined by the elementary class. This is the action that we use in order to define a 4D atom. A generic matter can always be decomposed in proper parts up to elementary level using the proper partude. And elementary can still be decomposed in temporal part. So we see the world as made of elementary particles, elementary parts. This is the perspective of physicists. But if you are a child, a kid, and you use Lego, for example, to build to have fun for yourself, then if you build an ontology for Lego, then the brick is the elementary object in your Lego ontology. So this approach is not peculiar to material science, but can be used also to build other ontologies with other type of purpose. Of course, the elementary, we cannot define materials by defining their elementaries. So we need to find a way to represent the groups of elementary that build a particular macro object in which we are interested in. But the logical path that we follow is to define the elementary and then to start to grow from elementary to bigger scale, because elementary is a very well it can be defined using logic in a very, very easy way. So we go to the smallest element possible, and then now we move towards bigger entities. So we need to find a way to categorize matter, generical matter entities, as a hierarchical composition of elementaries, because we need to define macro entities following a human perspective. We need composition rules to define the group of elementaries. But we need also to take into account the presence of vacuum between elementaries that composes a higher granularity level entity. The classical example is the atom, that is made mostly of vacuum instead of matter. So real matter in a human perspective is made predominantly of vacuum, interatomic space, the space between nucleus and electrons in atoms, space between molecules in a gas, and so on. So matter is something that should have inside itself elementaries and also vacuum. So vacuum is a space-time that has no elementary parts. This is the definition in our language of vacuum. So how can we define matter? matter is a general representation of group of elementary or group of other matter in a space-time, in an enclosed space-time. So this is matter. It can be partitioned as matter. This is matter. This is matter. This is matter, vacuum, matter. So the definition of matter that we propose is an object that for all its lifetime is made of something with matter, some elementaries. Can be matter or can be elementaries. So a matter is an elementary or a composition of other matter and vacuum without any vacuum intervals between its lifetime. So now we have here we are building a branch under space-time in which we can place the void, in which we have nothing, no field parts, physical, that is the union of field and matter. A field is a space-time that manifests the properties of a field. A vacuum is a space-time that has no matter, but still can have a field. A void is a vacuum that has no field parts, so nothing. And physical is equivalent to field and matter. Elementary are a particular subset of matter. So matter is always 4D. There is no 3D representation of matter. A 3D representation of matter is a geometry, is not matter itself. There can be a 3D slice of matter, but it's no more matter. It's a 3D special region. Because you can, just as like as you cannot cut your cake in infinitely thin slices, metal slices, you cannot divide in time your entity, your material entity, to an instant. There are always your matter can be sliced in time, but not up to an instant with zero extension in time. Boundaries and interfaces. You can here you can see matter A and matter B, which are in contact here, and we can define the boundary between two matter as another type of matter, which include part of matter A and part of matter B. So boundary can be defined as a matter, but the interface, which is another useful concept that we have in material science, can be defined as a geometrical entity that defines the separation between matter A and matter B. So by defining, by separating and by restricting matter to only 4D, only space-time, and leaving the geometry to other in the topology branches, we can easily distinguish between the boundary which is made of matter and the boundary which is made only of geometrical or topological entities. A physical is something that can be perceived as a matter of field. I already made you this example. But matter itself is very general. We need to find a more detailed way to describe different matter time, to include granularity. We did so by introducing a new partude, which is called direct partude, in which we drop the transitivity property, and we include this type of actions. In this way, we say that a nucleus, for example, is a direct part of atom, and proton is direct part of nucleus, but a proton is not a direct part of atom. So we define level of partude in order to help us to build definition of matter using a strict granularity hierarchy. You can see here an atom which is electron and nucleus, which is made of proton and neutron. And so the atoms has proper parts, all the elementary particles that constitute the atoms, but the direct parts of an atom are only 3, electron and nucleus. In this way, we can build a hierarchy, a granular hierarchy. But before to go in the direction of defining what our material branch, we need to define another concept, the concept of state. State stands for matter in a particular configurational state. Is defined as having special direct parts that persist throughout the lifetime of the whole, the state. So the state of an atom is this temporal part. This is not a state because we have a change in the partum. The same holds for the gases. The gases is a matter, but can be defined in states as long as we have molecules that are part of this gas or not. So state is a snapshot of a physical in a finite interval based on direct partum. So an existent also is another concept that we need to introduce, which can be defined as a matter that unfolds in time as a succession of state. So this is the final branch of the EMMO, in which we have a physical, matter, existent, state, and elementary. Let's go to granularity. Granularity is a particular class in which we collect the matter that is made of particular sub-component, direct sub-component. It is matter composed of specific type of object. For example, a granularity, an atom granularity is when you define a thing that is made of direct parted atoms only. This is the scope of these classes. But let's go to few examples. Okay, the time is over, but I'm asking for 5 minutes more for the examples. Let's have a look at examples here. Molecule formation example. The EMMO representation of molecule formation is represented by this process. This is a process of combination of oxygen and then dissociation. You can express this phenomena represent this phenomena in the EMMO by using two existent, atom 0 and atom 1, that lives their lives in this way. Or you can define it by states, by separating the existent in parts and having atom 0, state 0, atom 1, state 0, and then define these other states in which the atom is bonded by the atom 0 is bonded with atom 1. You need to define also the vacuum of this in order to have this as a single state. And then you can define, as soon as they dissociate, you can define the two states, separate states for atom 0 and atom 1. Or you can decide to represent this process using two states, at atom 0, atom 1, to define the state molecule and to define the states atom 2 and atom 3. And the molecule itself can be seen as a collection of states, atom 0, state 1, vacuum 0, and atom 1, state 1. In this way, we can express the molecule and the atom using temporal partud and spatial direct partud in a very unique and complete and generic way, so that we can have a hierarchy in which atom 0 and atom 1 does not share anything. This is another example of the difference between state and existence. For example, here you have a glass with water and ice. My drink is an existent, so this is an existent made of three states: water, ice, and glass. As long as my state, as long as a state does not lose direct parts, ice or water or glass, this is still a state. Ice, water, and glass are existent since they are the sum of several states. Their parts number is changing over time. But as soon as ice is totally melted, then my drink is no more a state. Okay, this is one state. This is another state. This is another state itself. As long as the drink loses parts, it changes states. So this is the first state, the second state, and the last state. But overall, this is an existent. Another example is the gas example. A set of molecules. It is not matter. This is simply a set. But as soon as you include also the vacuum that surrounds the molecules, then you can define a gas, which is molecules and vacuum. This is matter, and this is part of base. This is membership based. This is part of base. We also started to build a material ontology for the EMMO by using the continuum, mesoscopic, subatomic, and atomic entities, and the direct partude to build a draft, a raw material entity that can be used to describe entities of the real world. You can find details on this material ontology in the presentation if you want. I think that the time is really up. What we also have in the EMMO is also the definition of abstract items. Abstract items are a sign that lives in the ontological framework, are not real object entity, real world entities, are signs in the ontological dimension, and abstract can be used to define mathematical entities, equation, numbers, variable, algebraic equation, arithmetic equation, and so on, that can be used to define the physical model of that can be connected to a particular process in the material entity branch. In the abstract branch, we have also the natural law, that can be physical law or materials law, that can be expressed by mathematical equation. And we also have the properties that can be qualitative or quantitative, that can be used to characterize the material entities. And also the models which are equations that are categorized in meso, electronic, continuum, and atomistic. This is the abstract branch unfolded. The connection between the physical, the material branch, the property, the measurement, the modeling world is sketched in this slide, in which we, by using relation, we want to connect the material entity with its properties, and the properties with a mathematical representation of the properties, which is connected to the measurement, and connected also to the possible model that can be used to express, to calculate this particular variable. I think that's all, because I use all my time and also more than that. So if you have any question, we can try to answer them.
Yeah, thank you. yeah, it is open for questions, and if there are any questions around the abstract branches, we can also use that time to discuss that.
Yeah, there is a lot more information in the presentation that you can check it by yourself, that I had no time to present.
Yeah, and these slides are also available from the Brussels presentation, right?
Yeah.
Can I just maybe start with where are the slides available? We will send the information again. With the water ice case, just to say that the question of the states here evolving, the different states, is also a question of the granularity view of the level of granularity that is defined here. So we're looking here at water and ice and the glass, but if one was to look at just water molecules, for example, then there would be no change of state, at least for the first four items. At least for the first four.
Okay, I would disagree here. So the bound molecules go into unbound molecules, and so there is a change.
That is the question. So if you compare that with the slide that showed the oxygen molecules, would you then say it's the only thing that doesn't change is the existence, but you actually define different states between them, or would you say that the states remains the same? Emanuele.
So what I would say in the oxygen part is, in the molecule part, is that there become interactions and correlations which become active. So you've got independent things coming in, independent atoms which do not have correlations because they do not interact. And as soon as you go to the bound states, you get correlations, which may say that whatever some... so let me put the example I always tell. If you take the atom number 0 to be a state phi 0 and the atom number 1 to be a state phi 1, then these two states are independent. You can sum them up, and that is the system. So you end up at 1. But then you can square this equation, and you still have a system with the value 1, and you got interactions called phi 1 times phi 0, and that's the correlation.
I suppose the point I wanted to make, which is also a question, and Emanuele can maybe comment on that as well, is that what states we see and the evolution of states does depend on the granularity level.
Right, evolution at all. So a time step is a change in state, and that means that either the ice has vanished as on a macroscopic scale, that's a time step on the macro scale, something has happened. And if you go to higher temporal resolutions, you may see that one water molecule has left the ice and went into the water. So that's also a change. So that's an event. Yeah? So one can chop these events you're showing here not only into 3, so there is ice, there is only water, there is only glass, but you can have the first three, where there is ice, water, and glass. You can chop into other things in terms that you say that some molecules have left the ice and went into the water. So that's what happens there. So that's also an evolution, and you just know that there are smaller entities than the ice cubes, because otherwise the ice cube would not decrease while still being in existence.
But this is exactly what this example is showing.
I agree. But there is also an evolution of states between between the three first pictures.
No,
so
not
there is an evolution as soon as you increase granularity.
Yes, of course. This is correct. This is exactly what we want to do here. What we want to say here. Ice is losing direct parts. Ice is losing parts. They go from ice to water. So it means that ice is an existent made of several sub states. So when we say that my drink is made of 3 states, we are chopping the drink in time. We are slicing in time. So 3 states, it means 3. It comes in 3 ways in time. The first way is when you have water and ice and glass. The second is when you have water and glass. The third one is when you have only glass. And the part of drink are existent, not states, are existent. Ice is an existent. So it's made of substates. The substates last as long as one molecule of water, H2O, goes from ice to water.
Right.
So you're correct. This is it depends on the granularity level of the detail that you want to go through. If you want to stay at a human level without asking too much about molecules and atoms, looking at ice and water as a continuum, we have 3 states in my drink. But if you want to go in a meso perspective, then we can divide ice in smaller state. Is an existence divided in a smaller state. Then we can investigate a bit further what happens to the ice in terms of states. So each molecule that move from ice to water. But this is something much more detailed.
I agree.
So this is the powerful of this granularity perspective. You can neglect the complexity if you want, but if you want not to neglect, you can dig into it as much as you want. As much as you want. This is I try to explain this also in this example, because you can represent this process in very different way. It depends on what you want to focus on. For example, if you have classical molecular dynamics, you always have 2 atoms here, 2 oxygen atoms. You never have a molecule, because you have interatomic potentials here, and then you live only with atom. Okay, you can do post-processing, saying if the distance or the kinetic energy is lower than the potential energy of the binding energy, then you have a molecule here. You can do in post-processing. But in this view, we are doing classical molecular dynamics, in which we have an atom, oxygen atom, and another oxygen atom here, and they are still oxygen atom from the beginning to the end, and they have forces between them due to the interaction potential. Here we are doing mesoscopic modeling, in which as soon as oxygen 1 is reach oxygen 0 reach oxygen 1, then we change the object type, and the object is a molecule. So it is a meso object. And then something happens. The meso object is no more, and you have 2 atomic objects. This is another way to represent this process. The EMMO can give you the possibility to represent your process in these 2 ways. It depends on you. and you also can chop down this in the molecule in a subscale model. If you take this state and then you explode in and study it as atom, vacuum, and atom. So this is multigranular. It gives you a lot of freedom to represent things.
Okay. Yeah, thanks. Any other questions?
I have one.
Sorry, I want to underline also what Georg said about the bonding of the atom. The possibility for an atom to be standalone and to be bonded has been included in the atom branch. So an atom in the EMMO includes also the standalone atom, in which all the electrons are owned by a single nucleus, and also the possibility to having shared electrons between other nucleus. Okay, sorry.
When you discussed space-time, did you say that universe is not an instance of space-time, but it's a kind of class? Yeah.
You can see the universe as the biggest whole in which we and we are part of it. But this is a more philosophical statement than a useful one. You can always define. It means you can always define the biggest whole, and we are part of this whole in merological sense.
Yes, but that is an instance of space-time.
Sorry?
That is the biggest possible instance of space-time.
Yes. Yes.
Yeah. So it is instance. Good. Then
yes. It is not part of anything except itself, of course, and everything that exists is part of it. But this is not defined in the EMMO. Is not defined. It's more a philosophical statement.
Yeah. Sorry. Yeah, that was a simple question.
Okay.
I would also if you have time, please also consider the decision that we did to okay. Okay. The fact that a matter is a subclass of space-time is very different with respect to the BFO or other ontologies in which you have the place, the space, and the material entity occupies a space. This is not the case in the EMMO. The material entity is the space occupied by the material. Okay, this is a completely different perspective that helps us simplify a lot the relations between things and the distinction between geometry and matter. This is an important point that distinguishes the EMMO with respect to other ontologies. This has been the possibility to do this has been also discussed in the BFO, but not implemented.
Could you also, Emanuele, just comment and put your or share your view on what we're looking for in terms of the use cases, also for the discussion in the meeting in September, but also even if people cannot make it to that meeting, the type of challenges and use cases we're looking for. You could discuss that.
I would like to like the Keller.
Ja.
Okay. What we are looking in terms of user case for testing the applicability of the EMMO, we are looking to case. In this case, this is something I presented in Cambridge 1 year ago. Devices, processes, and materials as simple as possible. This is a very complex case, but we must focus to very simple case that can be expressed by using an ontology. So what we want to do is to collect user cases. So something like this one. So a plasma torch with powders that evaporates and then nucleates to form nanoparticles, something like this. But also simplest cases. For example, the dissociation, the combination dissociation of molecule is also a very important case. It's very simple, but it is very important. But also cases like this one, not so complex, that we would like to represent using the ontology. For example, here the nanoparticle phase can be represented like a continuum or like a set of nanoparticles, and the nanoparticles can be seen as a collection of atoms or a collection of nuclei and electrons, and so on. So what we want to do is to ask you to give us a very specific simulation case in terms of material, processes, or devices, also devices, that you would like to investigate and to be represented in an ontological way. Then we will try together to test the ontology and to build the part of the branches that are needed to address your particular user case. All the levels are welcome, from electronic, especially electronic, because there is a lot of work to do at this scale, and atomistic, meso, and also continuum are very, very welcome. This is what I try to do in Cambridge in order to show the possible application of ontology to a real world case.
Okay, thank you. Yeah, so that was also just as a reminder to please share these cases, and as I said before, hopefully you can make it to Cambridge, and please register for the meeting on the EMMC site. We sent the registration information earlier, but we'll also send it again. So are there any final questions before we finish the session? If that's not the case, then thank you very much. And as I said, we will make the recording also available.